So, we were deriving in the last lecture the Newton's law for viscosity in tensor form and the momentum conservation equation. Okay. Newton's law for viscosity is a relation between the stress and the rate of deformation tensor. Okay. So, I described for you the stress tensor sigma, which has two directions associated with it, okay. The direction of the force, okay, and the direction of the perpendicular to the surface. Okay. These are the two fundamental directions associated with the stress tensor. The force per unit area at a surface is equal to sigma dotted with n. Angular momentum conservation requires that sigma is symmetric tensor. In the absence of flow, there is a stress due to pressure. Pressure is compressive, acts along the inward unit normal. And therefore, the contribution due to the pressure is equal to minus p times the identity tensor plus a stress due to the velocity variations. The stress due to velocity variations has to necessarily be due to the gradients in the velocity or the variations in the velocity. The reason is because if there is a constant velocity for the entire medium, there is no relative deformation between nearby points. Therefore, there can be no internal stresses generated due to a constant velocity. Therefore, the stress has to be related to the gradients in the velocity or the variations in the velocity. If we further assume that the stress is related only to the is linearly related to the gradient in the velocity, then we can derive a relationship between the stress tensor and the rate of deformation tensor without having to make a reference to the underlying coordinate system. So, the velocity gradient tensor we had also analyzed. It has three components: an isotropic component, which gives you the radial compression or expansion from a point, okay, of nearby points relative to a point. That is the isotropic component. The symmetric traceless component, which is extensional strain, expansion along one axis, compression along the perpendicular axis, no net change in volume and no rotation of the axis. So, that is the symmetric traceless part. In 3 dimensions, the sum of the rates of expansion and compression are 0, that is the sum of the eigenvalues, and you could have expansion in 1 or 2 directions, compression in the others, and possibly no deformation along one direction. And then there is the antisymmetric part, which represents solid body rotation. I told you that the stress cannot depend upon the antisymmetric part, because when a solid body rotates, the distance between nearby points does not change. There is no deformation of the material, and therefore, there can be no internal stresses that are generated by solid body rotation. Okay. Therefore, you have two components. One is due to the symmetric traceless part, and the other is due to the isotropic part. For an incompressible flow, the isotropic part is identically 0. Therefore, the stress is only due to the symmetric traceless part, only due to extensional strain. Okay. And so, the constitutive relation that you get is of this form for an incompressible flow: a pressure which is isotropic and the shear stress which is related to the symmetric traceless part of the rate of deformation tensor. The sum of the diagonals is equal to 0. The divergence of the velocity is 0 for this tensor. Therefore, the isotropic part is only due to the pressure in the case of an incompressible flow. Okay. Yeah. And then we were trying to substitute that into the conservation equation in order to derive the momentum conservation equation, okay, for the fluid. Okay. So, the mass conservation equation I had written here. Okay. So, let me write it again. Okay. The mass conservation equation is of the form partial C by partial T plus the divergence of V C, okay, is equal to minus the divergence of J plus the source. Okay. That is the mass conservation equation. if you wrote the same equation for the momentum density instead of for the mass, okay, you would have just substituting the momentum density for the mass density. Just to highlight that there is a dot product between the gradient and one of those velocities there. Okay. Just to highlight that there is a dot product between the gradient and one of those velocities there. Okay. Now, the left side of this equation, the left side of this equation, I can use chain rule for differentiation. Okay. So, I can use chain rule for differentiation and I will get a rho times partial v by partial t plus v partial rho by partial t, okay, plus. Okay. I use chain rule for differentiation on the second term as well. Okay. So, I will get rho v dot grad v. Okay. The dot is between the velocity and the gradient here. Okay. Plus a second term which contains v times the divergence of v times rho. Okay. Okay, so those are the two terms in the expansion. Okay. Recall the momentum conservation equation for a compressible flow, okay, over here. Okay. So, therefore, these two terms can both be written together as v into partial rho by partial t plus divergence of rho v. Okay. That is the mass conservation equation plus a second term which is partial v by partial t plus v dot grad v. Okay. And this sums to 0 because of mass conservation, okay, because of this mass conservation equation here. Okay. So, the left side of the equation can be equivalently written as rho into partial v by partial t plus, let me write this a little more clearly. Okay, just to highlight that the dot product is between the velocity vector and the gradient, okay, is equal to minus the divergence of the stress tensor plus f. Okay. That is what you would expect in analogy with the mass conservation equation. And I should note that there is no negative sign here. Okay. There is no negative sign here either. Okay. Recall that the mass conservation equation contains a negative sign, and that is because the flux is defined to be positive if it is in the plus z direction. The flux Jz is, for example, positive if it is in the plus z direction. For momentum conservation, the stress is considered to be positive if the perpendicular to the surface is the outward unit normal, and because of that you do not have a negative sign in the expression for the stress. Okay. Because of that you do not have a negative sign in the divergence of the stress when you insert into the momentum conservation equation, because the stress basically increases the momentum of the volume below the surface if the outward unit normal is in the plus z direction, whereas the flux is defined to be positive if it is in the plus z direction and increases the mass in the volume above. Okay. So, that is the difference in the sign convention. So, sigma is equal to minus p times the identity tensor plus mu into grad v plus grad v transpose. Okay. Grad v transpose is with the rows and columns interchanged. Okay. Grad v transpose is the rows and columns interchanged. Okay. So, for grad v, I told you that the first index is due to the direction of variation. The second index is the direction of the velocity vector. Okay. In grad v, okay, this is the direction of the velocity vector, and this is the direction of the gradient. Okay. Whereas, in the transpose, the first index is the direction of the velocity vector and the second index is the direction of the gradient. Okay. And you are taking this dot product with respect to the first index. Okay. This dot product is being taken with respect to the first index. Okay. So, if I take the divergence, okay, of sigma, okay, what will I get? Okay. The first thing is minus, okay, del dot p I, okay, plus mu into plus del dot. Okay. So, let me just use colors to make the dot product clear. Okay. That is the divergence of the second term. So, let me I have missed out the viscosity here. Yes. Okay. Viscosity is a scalar. In this case, you are taking the divergence with respect to the first index. Okay. When you take it with respect to the transpose, okay, when you take it with respect to the transpose, okay, when you take the divergence of the transpose, okay, you interchange the rows and indices. You interchange the rows and indices. Therefore, you get the dot product with respect to the second index, okay, because you have interchanged the rows and indices, and therefore, the dot product will be with respect to the second, the velocity index. Okay. Okay, this is with respect to the second, the velocity index. Okay. The first term, the gradient, the divergence of the pressure, you can simplify it. Okay. Is going to be equal to Ex partial by partial x dotted with, okay, Ex p Ex, okay, plus Ey okay. And you can easily see this will just turn out to be Ex partial p by partial x plus Ey okay, so that is just the gradient of the pressure. Okay. Okay, just taking this dot product and you simplify it, Ex, Ey, Ez are independent of position. Okay. So, if you just take the dot product and simplify it, this is what you will get. Okay. So, the first term is just equal to minus the gradient of the pressure. Okay. The second term is okay, okay, and the third term is okay. So, this is the expression for the divergence of the stress in for a Newtonian fluid. If in addition the viscosity is independent of position, okay. If in addition the viscosity is a constant, okay. Okay, then this divergence of the stress is equal to minus the gradient of the pressure plus viscosity is a constant. So, I can take it out, okay, and I will get the dot product between the divergence and the gradient gives me del square, okay, V. Okay. The dot product between the divergence and the gradient gives me del square V, the Laplacian of the velocity vector. Okay. The second one, the dot product is between the divergence and the velocity. So, I will get mu into the gradient of the divergence of the velocity, okay, because the divergence is with respect to the velocity vector. And for an incompressible flow, this term is equal to 0. The divergence of the velocity is equal to 0 from the mass conservation condition. Okay. And this then is the divergence of the stress. Okay. This then is the divergence of the stress. Okay. So, substituting that into this conservation equation, okay, I will get rho into partial V by partial T plus V dot grad, okay. V is equal to minus grad P plus mu del square V, okay, plus F. This is the Navier-Stokes momentum conservation equation. Okay. This together with the mass conservation equation, okay, is a complete set of equations to determine the velocity and the pressure, okay, for an incompressible fluid with constant viscosity. Okay, for an incompressible fluid with constant viscosity. And you recall that I had also written the mass conservation equation for you, partial C by partial T plus the divergence of V C minus is equal to D del square C plus S. Okay. So, there is a difference here, okay, as you can see there is a difference between this term and this term, and also there is no equivalent of the pressure here. Okay. So, that is there is no equivalent of the pressure for mass conservation because the flux is a scalar. Okay. So, because of that there is no equivalent of the pressure in this case. Okay. So, note that the mass conservation equation is a scalar. Okay. The mass conservation equation is a scalar. The momentum conservation equation is a vector. It is a vector equation for the vector velocity v. It has 3 different components for Vx, Vy and Vz. Okay. 3 different components for Vx, Vy and Vz. So, there is one vector equation, which is 3 scalar equations, plus 1 scalar equation for mass conservation, divergence of velocity is equal to 0. And there are 4 unknowns, the 3 components of the velocity plus the pressure. Okay. So, there are 4 unknowns, the 3 components of the velocity plus the pressure. So, those 4 unknowns are determined from these 1 vector plus 1 scalar equation or 4 scalar equations. Okay. So, these are the Navier-Stokes mass and momentum conservation equations. And the important point to note here, as I have highlighted with my red color, is that in this inertial term on the left, okay, the inertial terms on the left, the pressure and the viscous terms on the right. In the inertial term on the left, the dot product is between V and the gradient, okay, and the direction is the direction of the black V, okay, on the right side. So, the derivative acts on V, okay, the gradient acts on V to give you a second order tensor, that is the rate of deformation tensor, and the velocity V dotted with that rate of deformation tensor is the second term in the is the nonlinear convective term on the left. And as I had explained earlier, this V dot grad V is a nonlinear term in the velocity, and because of that this equation is a nonlinear equation for the velocity, and because of that you could get multiple solutions. One of the solutions is the laminar flow, but there are other solutions. The laminar solution becomes unstable when, for example, the Reynolds number exceeds a critical value, and the system spontaneously goes to another solution, which is the turbulent solution, and both of these are solutions of the same conservation equation. The second thing that I had told you earlier was that the dynamical pressure, okay, only variations in the dynamical pressure affect the flow field, okay, or as you can see from these equations, the momentum equation depends only upon the gradients in the pressure. Okay. So, you can add a constant value to the pressure everywhere in the field and the velocity field will not change, okay, because it depends only on the dynamical pressure, variations in the pressure. Okay. So, that is the difference between the dynamical pressure and the thermodynamic pressure. The velocity fields depend only upon variations in the dynamical pressure. And finally, a simplification of this in the limit of high Reynolds number. You recall we had discussed potential flow, okay, as incompressible okay, inviscid and irrotational. Incompressible, inviscid and irrotational. Okay. Irrotational means the vorticity is equal to 0. Okay. Inviscid means the viscosity is equal to 0. Okay. And incompressible is constant density. Okay. So, in this limit, if I simplify the equation, okay, I will get rho into partial V by partial T plus V dot grad V plus F. Okay. I neglect the viscosity here because it is inviscid, okay, and it is irrotational and it is incompressible. If a velocity satisfies this irrotational condition, then this velocity can always be expressed as the gradient of a potential, okay, of a velocity potential, okay, because there is an identity that the curl of the gradient of any scalar function has to be equal to 0. Okay. So, for an irrotational flow, you can express the velocity as the gradient of a potential, a velocity potential. Okay. And if you look at this term, right, V dot grad V, okay, If it is irrotational, the velocity gradient tensor is symmetric. Okay. If it is irrotational, the velocity gradient tensor is symmetric. Okay. So, okay. The velocity gradient tensor is symmetric, the rate of deformation tensor is symmetric. What that means is that grad V is equal to grad V transpose. Okay. If the rate of deformation tensor is symmetric, for its irrotational flow, the antisymmetric part is 0 because the vorticity is 0 and the rate of deformation tensor is symmetric. Okay. That means that grad V is equal to grad V transpose. So, I can as well write this as a dot product, okay, between whole transpose. Okay. In which case the dot product is between the velocity and the velocity. Okay. The gradient is the direction of the vector. Okay. And you can show by just expanding this out, I will leave it as an exercise, that this is equal to the gradient of half v dot v, okay, half v square. V dot v is the square of the magnitude of the velocity. Okay. So, in this case the momentum conservation equation becomes rho into partial by partial t of grad phi v, okay, substituting this expression for the velocity, okay, plus, okay, grad of half v dot v, okay, is equal to minus grad p plus f. Okay. And if the force F is conservative, then it can be written as the gradient of a potential. Okay. F is equal to minus the gradient of a potential. Okay. So, this can be written as minus the gradient of some potential, okay, if it is a conservative force. Okay. And since the density is a constant and you can interchange the time and spatial derivatives, I can write this as grad of rho partial phi v by partial t plus half rho v square, okay, where v square is v dot v is equal to minus grad of p plus phi, okay, where this capital phi is the velocity, is the potential for the force. I have written the force as minus the derivative of a potential. Okay. And taking everything to the left side, I get grad of rho into partial phi v by partial t plus half rho v square plus p plus this potential is equal to 0. And when the gradient of a function is 0 throughout the domain, that means that that function has to be a constant. Okay. When the gradient of this function is 0 throughout the domain, that means that that function has to be a constant. Okay. So, rho partial phi v potential by partial t plus half rho v square plus p plus the potential phi has got to be equal to p naught. If you recall, this is the Bernoulli equation that we had. If the potential in a gravitational field is equal to rho g z, where z is the direction opposite to gravity, or in a rotational field is half rho omega square, okay, r. Okay. Okay. If it is in a centrifugal field. Okay. So, this is the same Bernoulli equation that we had without this time derivative term, okay, without this time derivative term. Therefore, that equation that we used is applicable for a steady flow. If it is unsteady, then this additional time derivative has to be included. Okay. So, this is the derivation of the Bernoulli equation from the Navier-Stokes momentum equation for an inviscid irrotational incompressible flow or a potential flow. This has to be combined with the mass conservation equation. The mass conservation equation is del dot V is equal to 0, which implies that del dot the gradient of the potential is equal to 0 or del square phi V equal to 0. Okay. So, that is the mass conservation equation combined with the momentum conservation equation, which is the Bernoulli equation for an inviscid irrotation flow. So, this completes our derivation or our justification for the Navier-Stokes mass and momentum conservation equations for an incompressible fluid with constant viscosity. Okay. So, I have written it for you in vector form, the momentum conservation equation in vector form, and the mass conservation equation just states that the divergence of the velocity is equal to 0. Next time we will examine how to use these equations to solve problems in limiting cases, the first where diffusion is dominant and the second where convection is dominant. So, these two we will examine in the following lectures. This completes our derivation of conservation equations, first for mass, then for heat, and then for momentum. And for momentum we had to take a little bit of a detour because we had to define the tensors, the stress tensor and the rate of deformation tensor, and write the constitutive relation as a relation between these two tensors, and then substitute that into the momentum conservation condition to get the Navier-Stokes equations, mass and momentum conservation for a Newtonian fluid for an incompressible flow with constant viscosity. We will go on to analyzing specific cases in the next lecture. I will see you then.